All right. Excuse me. So your programming test, I already got a preliminary result from the TA. I just need some time to really generate the feedback, etc. You can definitely expect to get back to me, hear from me before next class. I'll return back to you the feedback. And then I will try to see if I can arrange maybe some TA hours. So for those of you who actually want to go over your submitted maybe model in event B, maybe I can schedule some TA hours to do that, right? I'll try to schedule several slots, so definitely you guys can choose. I'll get in touch with you, don't worry. And your written test number 1, I'll definitely release by early Monday. I just gotta check usually some stuff before I release it. But you'll definitely get both of them back by Tuesday next week. Any question about the course? And I know your lab number 3 is not yet released. I'll do that, and then I'll adjust the deadline accordingly, right? So you definitely get enough time to look at the contents. Okay. All right, so let's now do a quick recap. Oh, Diego.
Sorry, just one quick question if you don't mind. How influential would you say the programming test material is going to be on the final exam?
Okay, fair question. I would say the exam might contain certain parts that might also ask you to develop some machine, kind of, right? So maybe there might be part A, part B, part C. Maybe part A, we kind of ask you to declare variables of certain type. Maybe you got to choose either it should be a partial function, relation, etc. They might impact to some extent. But what might be the best way to really prepare for that part of the exam? You definitely want to go over the practice test, especially the one from fall 24. The employer, that one. I think that one's definitely going to help, right? Good. Right, I can definitely speak more about the exam, maybe a little bit later. Okay. All right, let's now do a quick recap, and then we'll move on to a little bit more interesting stuff today. We're going to do another thing called inference rule today. That's going to be very, hopefully, interesting. Okay. All right, we spoke about transition of events last time. So that one there is just another example of considering pre and post states. The conclusion is, let's say for this particular event called withdrawal right here, right? The before-after predicate can be converted into this. So we got the balance function B prime is equal to this particular expression, right? So now we want to think about if you got some proof obligation where the goal over here is to say the invariant should be preserved in the post states. How do we express that? The way to express that is you're actually going to take the original invariance right here and then substitute every occurrence of the balance function by the B prime, basically. And B prime, we know that is actually exactly equal to this. So that's why you saw me doing this and this replacement, right? So please review that particular part. So this one here, just a little bit more complicated replacement, but the principle is the same. We're going to do this kind of a replacement quite often, just to figure out the proof obligation. All right. And then we spoke, okay, so that's and then we got the test 1 review as well, but that part I wouldn't recap. So this was really the last thing we did, okay? So that one, you just gotta remember this slide here, keep it handy to you. Right here, sorry, right here. So it would be slide number 18, okay? So this summarizes all the components you will see in a single proof obligation rule. So the rule itself is going to tell you how exactly you can generate the corresponding proof obligation. We'll do exercise right away. Okay? So I wouldn't repeat. Oh, actually, let's repeat very quickly. Okay? So we got basically all these quickly. We got the list of constants. We got also axioms. We got variables in the pre and post states. And also we got the invariants. Also, we got the guards of the events. Also, we got the effects of the event. Think about the effects over here would just be the right-hand side of the before-after predicate, the right-hand side, okay? And then we got, finally, the before-after predicate, right? So these are the things you will see in some proof obligation rule. And let's now dive into something that will apply this right away. But before that, any questions? All right, sounds good? Okay. So that's about the written test 1 review. Okay, let me show you the slides. Now we are on to slide number 19, okay? Let's now consider the proof obligation rule. So So the rule itself is going to be presented using some sequence notation, like a turnstile. However, the rule itself is not really exactly the sequence. Somehow it will have to be instantiated into several sequences that we can prove. But I'll show it to you. So this is the first rule we're going to consider. All right, I'm going to dive into it in detail. Every symbol over there we mentioned, like A, I, G, and also I with subscript I, is something we kind of mentioned in the previous slides in the formal component. I'll review it. Okay, let's take a look. All right, so let's now take a look at this. So this is your first proof obligation rule for invariant preservation. Okay, let's now talk about this one here. Right, you can see this part here. Okay, this part here tells you that you should really collect all the axioms. Okay, so just this part over here tells you that you should collect all the axioms. And this part here tells you that you should really collect all the invariants and then express them in the pre-state version. Okay, so this will be the pre-states version of the invariance. And finally, this will be the guard. However, the G over here does not refer to all the guards of all the events. It only refers to the guards of a particular events, okay, depending on how many events you have. For example, let's say the G here may refer to the guard of ML out. In this case, it's simply just true. And also, the G here may also refer to the guard for ML in, which is also happen to be true, right? So it depends. Okay, let me write it down. So the guard over here refer to the guards of some events, which may be ML out, it may also be ML in. All right. So finally, you can see all the things we have described so far, they are actually above the turnstile. So that means these are the assumptions we can make. But what do we want to prove? What we want to prove is here. We want to somehow prove the post-state version, because the post-state has to include the effects of the before-after predicate, right? So this will be the effects. So you can think about this part over here is the effects. Effects of the event's action. So overall, this one here is really talking about the post-state version of invariance. And for any one of you with a sharp eye, can you see this a little bit difference here? You can see the I here is just I. Here, the I here has an index I, right? There's a subtle difference over here. When you assume the truthfulness, when you assume that the invariant is actually true in the pre-states, you assume all the invariants are true. So first of all, so this part here tells you that we assume, okay, let me just write better. We assume all the invariants hold in the pre-states, which means we assume this invariant is true and this invariant is also true. We assume all of them collectively. However, what we want to prove over here, we only prove one invariant at a time. We don't really try to prove all the invariants at one go. We do it a little bit like a divide and conquer. Okay. So this one here, this I over here is telling us as a goal, prove invariance at index I. And in our particular case, you can see the index could be either 1 or 2, okay? Which can be 1 or 2 in our model. So we assume all the invariants hold in the pre-states. What we want to show is a single invariance is actually preserved in the post-state, and we do that individually. right? So here is a follow-up question, and then we try to do it together. This is only a rule, even though the rule actually uses turnstile. This rule actually tells you that there is a number of proof obligation. Each one of them will be specified as a sequence, and they need to be proof, all of them. Okay, so now the question is, how many exactly do we have? How many sequence? Okay, I think at this turn here, how many sequence for invariant preservation based on this? Right, we got to figure out. Okay, and this is your first exercise. I'm going to dive into it, just tell you the reasoning. Since we consider all the axioms collectively, there's no variation here. Also, we consider all the invariants at one go. There's no variation. However, this one here has some variation. This guard here may refer to ML out, or it may refer to ML in. So there are two possibilities, right? And also, this one here, we talk about all the invariants, we talk about single invariants in the post states. And this I here can either be 1 or 2. So you can see somehow we have to figure out the combinations of the proof of all these factors. Okay, let's now put them out. Okay, I'll put this as a star. So this refers to the guards of some events. Okay, we're going to enumerate out all the possibility. It could be the guard for ML out. It could be the guard for ML in. So this can be either ML out or it could be ML in. So we got two possibilities. All right. Another variation point is here about the index of the event. So we only want to prove one invariant at a time in the post states. So the excuse me. So the star over here, some invariant condition. And that one there is going to be, I'll write it out, it's invariant 0, 1. So the one with index 1. Or invariant 0, 2. So we also got two of them. You got to think about all the factors. Sometimes we may have even 3 factors, so it really depends. All right? So the total number of proof obligation. So the total number of proof obligation or sequence for each one of them will be 2 times 2. And I will enumerate them out together with you just to see the idea. So this will be something very important for you to note. So when you look at the proof obligation rule, it's a very general one. But that one there might suggest several variation points, in which case you have to figure out multiple sequence. And Roden actually look at this rule and try to generate this, the list of possible proof obligation. Okay. All right, so now let me just do another page over here. And let's now figure out systematically. Okay. So let me copy this. Right here. Okay, the same thing right here. Which 4? All right, let's now, so there will be 4 proof obligation. And we also have some naming convention as well. So let's now be systematic. There will be 4 of them. So we got proof obligation number 1, number 2, number 3, and number 4. Let's just take maybe ML out for example. ML out, for example. Okay? So we start with, let me talk about the label for the proof obligation, and we'll see the actual contents. So to start with, we got ML out. So that's the events. And then you put a /, right? It's part of the name. And then for ML out, we choose a value for I. Let's say we choose index 1. In that way, we got invariance 0 and then 1. And what we are trying to concentrating right now is about invariant preservation. And we just put I and V. So this one here is about invariance preservation. invariance preservation. Okay, that's the very first one, but we haven't seen exactly it is. Okay. All right, the second one here. So we got ML out for the same events. And then we may want to prove about the maintenance of a different invariance. You can see for the same events, ML out, we may want to prove 1 and 2 separately. And that is also about invariance preservation. Okay. How about 3 and 4? So now you can kind of see what 3 and 4 should be, right? So we already kind of exhausted the possibility for ML out, which can be for invariant 1 or 2. We haven't done anything about MLN, right? So why don't we do that? So for MLN, the events, so we start with MLN. And then invariance 0, 1, and about preservation. And also for the same events. And we now try to do for index 2. Invariance 0, and then 2, and then invariance. All right? So these are the 4 proof obligations that will be generated systematically, right? So based on this rule over here, we figure out these are the 4 proof obligation. Question?
So how come there's only 4 and not 6 for like ML in with the axiom and ML out with the axiom?
Because, okay, so the question was, so you can see here we kind of consider all the axioms as a single unit, so there's no variation over there. But actually also for invariant over here, there's also no variation. The only 2 places we got variations is about which guard are we talking about, which events basically, and also which index of the invariance. So these are only 2 things. You can think about this part here, MLL or MLN, kind of correspond to the variation over here. And also here, invariance 0, 1, or 2 correspond to the index over here. So we kind of try to figure out the combinations. Okay, a very quick check with you, all right? Let's say, for example, if I add another invariance 0 and 3, something, how many proof obligations should I add? Oh, how many I should add 2, right? But in total, you'll be 6, right? Okay, so now that means I got PO5 and also PO6, right? Because this ought to be proved with respect to ML out and ML in, right? So ML out, and then invariance 0, 3, and then about preservation. And also ML out, invariance 0, 3. And then invariance. I got 6 in total, right? Yeah. Sorry? PO6. You mean over here? Okay, I can rewrite it. ML in. Yes, I agree. Thank you. Absolutely. Thank you. Good. All right. Let's now move on. Let's see how we can actually specify it. Okay. Just before that, let me just say one more thing. Okay. Whenever you see the IMV, let me say a little bit more detail about it. So when you see something like a ML out, and also, for example, invariance 0, 1, and also invariant, right? So this part here really means that the proof obligation is related to whether or not taking a state transition, right? We talk about pre-state and post-state transition. A state transition via some event action, right? They got the before-after predicate. Can preserve, or you can say maintain, this particular invariance. Okay, that's really the precise meaning. Okay, complete. All right. And we'll focus on invariant preservation just for today. We'll see some other invariant, some other proof obligation as well. All right, let's now try to see how we can, since we know there will be 4 in total proof obligation. So let's see which 4, how exactly we can do them, right? That's something we pretty much did earlier, but let me just do once more quickly. So let's say I should do two of them. The other 2 you can do as exercise. So let's say we got PO1, which is the ML out / invariance 01 and also IMV. Okay, I'll put these 2 in parallel so you can see they will share quite a bit of a part in common. Only the variation part is going to be different. Okay, PO2 and then ML out and then invariance 02 and invariance. Okay, since we are talking about ML out right here, all right, ML out, and then ML out has the guard true. Okay, right here. Okay, I just put some annotation here. Let's go one by one. The first part is about the axiom. This one has no variation, so 2 of them will share the same. So you simply put D is a natural number. And also here, you also put D is a natural number. So this part here is really the same. It's like a common hypothesis between the 2 proof obligation. And the second part is about the invariance, all the invariants in the pre-states. So that means we're going to include all of them. This one also has no variation. Okay. So here we got N is a natural number, N less than or equal to D. N is a natural number, and also N is less than or equal to D. Right? Now, next part. Next part there does have some variation. Over here, let me make it slightly more interesting. Okay? So let's say rather than considering ML out, why don't we consider ML in, right? Okay, let's say that. If I put ML in over here, right? So that means this part over here, I'm actually going to put a guard for ML out. I know that it is true for now. And for this part over here, I need to put a guard for MLN, which just happened to be true as well. But it will not be the case anymore later. We're going to fix them later, okay? Not for now, okay? So I'll just use the color just to show to you, right? Okay? Since here we talk about MLN, talk about its guard. We talk about ML out, we talk about its guard, all right? And then we got a turnstile right here, right here. So what we should do now is we got to do the invariance, right? So this part here is just another variation, right? And the invariant we're talking about is one of them is this, the other one is this. All right, so now let's do it carefully, okay? So as I said, since you haven't really done lots of exercises, maybe the safest way to really go for it is, first of all, copy down the corresponding invariants. It's going to be invariant 1 for PO1, invariant 2 for PO2. Let's copy first, okay? And then we'll make the post-state version. Question?
Aren't we using the wrong ingredients for the ML out for the first one? It should be N belongs to the natural number, because we are using invariant 0, 1.
So 0, 1?
For the first part?
You mean that's an axiom?
No, I'm talking about the invariants. You should be using the first one, right?
Sorry, say it again. You're talking about this one here?
Yes.
Okay, yeah, so just this proof obligation, I'm trying to say that ML out is going to preserve this particular invariance. And this one here, I'm saying ML in should preserve this particular invariant. I'm trying to show to you 2 proof obligation where you got different concern and how we figure out exactly how to write them. That's what I'm trying to show here. Of course, here I'm only including 2 possibilities. I already left 2 things out. That's something you can also try as well.
No, but in the previous statement you said we are using for the first one.
Yeah, maybe the sequencing is not exactly the same. So here I just use one way to really enumerate them. So here I just try to change the order a bit. Yeah, just to illustrate. Okay, not exactly the same order. Okay, well, okay. Let me just continue, and then I will just tell you what the other twos are, so you will see. Okay. All right. So now the first one there is concerning about invariance 0, 1, which is right here. So what I will do is I'm going to do n is a natural number. First of all, copy that down. Okay. And then for this one here, invariant 2. So I'm going to copy that down as well. It's going to be n less than or equal to d. Okay. So step number 1, copy the invariance. Number 2, adapt it to be a post-state invariance to the post-state version. In which case, I can use a different color. I can just prime the variable. Since I know ML out is only trying to modify n, and also ML in is only trying to modify n. So I just need to prime, like that. All right, second step. Question?
In your example, there's no like guards there, but I know that you wrote true, but like let's say you had a guard, would you also just write what it evaluates to, or would you write the guard?
You will write a guard, yeah. That's a very good question. So let's say, hypothetically, let's say for ML out right here, rather than guardless, right? Yeah, I might put something like maybe n larger than d, whatever. If I say that, so I should really put n larger than d right here. Yeah, just copy that verbatim. Okay. All right, so second step is to adapt it to the post-state version, and number 3 will be to really substitute it. So number 3 will be substitute each prime variable using the before-after predicate. Because for this one here, the before-after predicate is n prime equals n plus 1. And this one here, the before-after predicate is n prime equals n minus 1. So now I can do this one here, do the right replacement. That's for ML out. I should really do n plus 1. And for this one here, it's ML in. It should be n minus 1. All right. Right? Questions? Okay, just get more and more used to how we create the actual sequence, right? You need to know what sequence to prove first, but to really figure that out, you will have to look at the inference rule and to really understand what exactly it is trying to say. So what have we left out, basically, right? So I can put some little box over here, suggest something you can definitely try as an exercise. Should be easy for you to do on the paper, okay? I'll put exercise here. Exercises. So, for example, PO3 could be, for ML out, I have already handled invariance 0, 1. I should handle invariance 0, 2 as well. So ML, okay, I'll write better. ML out. Invariance 0, 2, and then IMV. And PO4 would be, since I only handle invariance 0, 2, I should handle invariance 0, 1. So that'll be ML in, right? For this events, invariance 0, 1, and then invariant. All right. So guys, give it a try. That should be rather easy to state them. Okay. But you will see the solution anyway on the slides. All right. Any questions? Okay. I would suggest we go over a little bit more definition about inference rule, and then we can take a short break. Okay. Just 6 minutes. Yeah, about 5 minutes or so. So now we are done with slide number 19, okay, just about the inference rule. And so before claiming that your model is actually correct, so all the proof obligation will have to be proved and discharged. So we will see invariant preservation, we will see invariant establishment about like initialization. Also the interesting bit we're going to see maybe next Thursday will be deadlock freedom. It's going to be the interesting proof obligation to understand and prove. Okay? Usually that will be the tricky one to actually prove. But we'll go over that. All right. So next slide. Let's talk about inference rule. Okay. I would suggest I will just go over the syntax like a meaning like last time when I first introduced sequence, and then we'll take a break. After the break, we can try to compare the two things because they might seem a little bit confusing at first. Okay, let's see. Let me just go directly to the syntax, right? So you can see that. Oh, sorry. Right here. Right here. Okay. This is something definitely different, right? You don't have turnstile. Instead, you have a horizontal bar. All right? And that's the only way you can present the inference rule. You cannot do anything like this. You cannot do it. All right? Just to let you know. So the syntax goes like this. So let's start from this basic. L here is a label. So this will be the name of the inference rule. And we'll see lots of them today. Okay, that's the name. And then above the horizontal bar, this one here is something called the antecedents. And this one here, notice something very carefully. What can that be? A is going to be a set of sequence. Two things to note. Number one, it's going to be a set, which means it may be empty. So the A here may be just completely empty set, right? It's a special case, which we'll talk about. And also, if you do have something in A, each one of them is going to be a single sequence. And we'll see example very soon, okay? And then what about C here, underneath the vertical bar? Sorry, horizontal bar. That's what I meant to say. So this one here is called consequent. And not a set anymore. It's a single sequence. You have no choice. A single one. Not more, not less. A single sequence. Let me give you one example right away, but we'll talk about what exactly it means a little bit later. Okay, one example. This is something you will see also after the break. So let's first of all draw the horizontal bar. The rule is called MON, standing for monotonicity. Monotony. You may have heard about this term, maybe in the 1090, maybe. Okay, well, we'll talk about it, don't worry. Monotonicity, MON. This arguably will be the rule you use the most frequently, especially as the first step, you will see. Okay, so now, here is going to be a set. Here is going to be a set of sequence. I can just put one, which is a singleton set. I can simply say, for example, a sequence H1 turnstile G. It's a single sequence, right? So for this one here, you can think about it's more like a singleton set. Singleton set of sequence. All right. On the other hand, underneath the horizontal bar, we have the consequent. In this case, I say H1, also H2, turnstile G. All right. So this part over here is a single sequence, single one. It's only about syntax. So you will see many rules. I'll give you a little bit preview very quickly, right? So that's something we'll go over after the break. So these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the first 10 inference rules we're going to go over. Okay? But of course, in the written test number 2, and also in the written test 2, I'll provide this page to you. You don't need to memorize it, but at least get get familiar with the rule. For the exam, you will just have to put the ones you need on your data sheets. Okay? All right, let's now talk very quickly about what it really means. Semantics. When I write A as the antecedent and C as a consequence, what does that really mean? It means the following. That means the antecedent implies the consequence is equivalent to true. Meaning that we are not really trying to prove something over here. It's something tell you that it's really true. We are telling you that A implies C is a theorem. You don't need to prove it. Okay, I'll compare this with the sequence maybe after the break. Okay, for now, just understand that inference rule is a rule. It's not something you want to prove. You can apply that to really do some other proof. Okay, and some very quick and there are different ways you can interpret that, but this is something I would suggest you can give a try to get used to. The meaning is to prove the consequence C. It is sufficient to prove the antecedents A instead. If you look at the implication, since we know the implication is a theorem, so if you are able to prove that A is the case, it will follow C, right? So now if I really want to prove C, I don't really need to prove C directly. I only need to prove A directly, because once A is proved, C will just follow, right? So this might be some informal meaning you can kind of remember, all right? So I'll highlight it, and then I'll just talk about this particular example, okay? And then we'll take a short break. So this is about the meaning here. And then let's see this one here. How do we interpret this? This is saying, if I want to prove this particular sequence with two hypotheses, H1 and H2, it would be sufficient for me to prove this sequence instead, which has the same goal, but it has only one hypothesis. I drop some hypothesis, basically. If I want to prove something given two hypotheses, it would be equally good if I can just prove with a single hypothesis. That would be fine. But you cannot go the other way around. You cannot just keep adding hypotheses. All right? I'll write it down. So this one here is going to be interpreted as to prove H1, H2 until G. It is sufficient to prove H1, G. That is, we can drop hypothesis. We can drop as many hypotheses as you like. Okay, that's very important, but we'll see more about the monotonicity rule. All right, one final fact. What does it really mean when the antecedent here is simply empty? All right, so let me write it. Okay. So this one here, if I simply write an inference rule like this, I simply say I got some consequence over here, and then I got some label. No antecedents. What does that mean? If you kind of follow the pattern, when I got C and A here, I said in order to prove C, it would be sufficient to prove A. Right? Yeah, pretty much, right? Good, okay. So now, the meaning of this really is, as your fellow student said, I'll write it down. So this one is really equivalent to, with the same consequence over here, I simply say true. In order to prove C, it will be sufficient to prove true. True is always just proof automatically. That means in order to show C, you don't need to prove anything. It's already true. So this is a way to show that C is an axiom. All right? So this means C is an axiom without any proof necessary. All right. This will be a very quick summary and facts and a little bit basic property about inference rule. Let's take a very short break. I'll answer your question maybe after the break. Okay. Yeah. And then after the break, we'll compare sequence and inference rule. All right. Please get your iClicker ready. So one more thing I want to say, I forgot, it's actually on my notes. So when we spoke about the intuitive meaning of inference rule, we say that to prove the consequence C, it would be sufficient to prove the antecedent A instead. So the instead over here suggests that your proof is just going to be a series of rewriting one sequence into another, for example. Right? So just say this instead over here really suggests there will be quite a bit of rewriting to be done. But I'll explain what rewriting is. We'll see. Rewriting of this one from one sequence to another. Yeah, Diego.
So I just have a question. So coming back to the special case when A is empty or absent, right? I don't see really how, if that's the case, if we have an empty antecedent, how is that not preventing us from disproving anything?
So let's say this. Alternatively, if you say this is equivalent to, let's say this, the same consequence by proof false over here. By the definition, to really prove this, it would be sufficient to prove false. You can never prove false.
Right, but we're saying that if it's empty, then it's true.
It's actually true, yeah, it's by definition.
So what is preventing me from putting any consequence I want if I have an empty?
Yeah, so this means if I give you a rule, okay, let's say for example, okay, I see what you mean. Let's see one example, concrete one. How about this one here? Okay, this one here. The rule is called P1. You can see this guy here is a consequent. It's a single sequence. The sequence simply say, I want to prove that 0 is a natural number. The rule tells you that to prove it, it would be sufficient to prove true. That means this particular sequence right here is an axiom. 0 is always a natural number. So that's what the rule is telling you.
Okay, but I still don't see how you can just put any other statement on the consequence.
How about delay that a little bit? Maybe let me try to clarify maybe with you after class, make sure I really understand. Okay, sure. Maybe that will clarify itself pretty soon. Okay, well, otherwise we can revisit. Okay. All right, let me do a very quick comparison for all of us just to make sure we understand about the syntax and also meaning for sequence versus inference rule. They are very closely related. They got to work together very closely, but you got to make sure they are still not exactly the same thing. So first of all, let's start with sequence, which we spoke about. Okay, for sequence, and we know that we can present vertically. Let's say we do that. H entails G right here. And this may or may not be a theorem. That's something we want to prove. All right? So this has the meaning of H implies G. And of course, this is subject to proof. If you cannot prove it, either because you haven't really got applied the inference rule properly, or simply because there's something wrong with your sequence itself, which you got to fix. Okay? And inference rule. And for the inference rule, so what we have is we got horizontal bar right here. We got antecedents, we got consequence, and we got some label. All right, like that. Okay. this simply means A implies C is equivalent to true. You don't need to do any proof. However, you might apply this one here in other proof step. All right? So this means this may be used as a proof step. We'll see. Okay? I just want to write it down. Another way to say that, to make progress, in proofs, we can rewrite the consequence C as A, meaning that we want to prove C, but the rule tells me I can just prove A instead. So I simply rewrite from C to A by this rule. Okay, one example right away. Okay, remember this one here, right? Monotonicity. What does that one really mean? Okay, that one really means if I have a sequence, if I want to now prove H1 and H2 given as a hypothesis, I want to prove the goal. Let's say this is the sequence I want to prove. Okay, you can think about this is the sequence I want to prove. If I want to prove it, I notice that I find that maybe hypothesis H2 is not so relevant. I can drop it. The reason that I can drop it is by that monotonicity rule. So I can simply apply monotonicity, and after that, I will just prove another sequence instead. Okay, so I can drop H2, H1 instead, and G. So this is a single proof step. Not exactly complete, but just a single step. I wanted to prove this particular sequence, but by the monotonicity rule, I can simply drop H2, and I can just prove another sequence instead. That's what I'm doing here. All right? Okay. But we'll do many things like this. Okay. And of course, this one here is something assumed to be true. Okay. Assumed to be true. To be true. All right. Okay, let's see some example here. What would be the general steps to really prove, right? So what I'm talking about right now would be, so we are now done with slide number 20. And we are now going to talk about slide number 21. Okay? Think about what's the general steps and structure. Let's go over that. Okay? Let me just read off the slide a little bit very quickly, and I'll give you an example. Let's say, for example, I want to prove this particular sequence. I want to prove it. Okay? You can see the naming convention here, ML out, and also the invariance and IMV, right? That's something we did earlier. Let's say this is a secret I want to prove about invariant preservation. Okay? In order to prove it, I need several steps, at least one step to really prove it. Okay? So here's a general pattern you'll get used to. You want to apply some inference rule. And the inference rule is going to actually rewrite the consequence as the antecedents, right? So it's going to transform some sequence into another that we want to prove. And then you got to keep doing this until the last sequence you want to prove itself is an axiom, according to some inference rule. All right, so these are the two general principles, but we're going to see exactly how that can be applied. Okay, let's take a look at this. All right. So let's say we know these two inference rule, let's say, but let's not worry about what exactly they mean. You know, we're going to see more, okay? But this one we already saw, right? So think about this one here. It's about rewriting. And this one here is more what I call base case. You think about, let's say you're executing recursion in Java. When do you know it's time to really your recursion is going to terminate? When you reach the base case, right? So think about when you're doing a sequence proof, you might keep rewriting using different rule. but it cannot go forever. It's got to terminate at some point. As soon as you hit some base case, you know that it's going to terminate, okay, roughly speaking. Okay, let's now try to look at this one here, okay, carefully. This is something we want to prove, okay? So we start with that. So I'm going to make a copy here, and I'll show you what we're going to do a lot for the rest of the semester. All right, so I start with this, leftmost, okay? Usually just go from left all the way to the right. And usually, when you start with, write down some also advice you can also try. You want to analyze the go predicates. This is the go predicate I'm talking about, right? That's the go. The go predicate to prove. And then ask yourself the following two questions. Question number one. What are the relevant variables? And number two, what hypotheses might be useful for me to assume in order to prove the goal? What hypotheses are useful? Are useful. Okay, so these two are very general questions, but that can kind of help you, right? Because sometimes you might see some sequence that's kind of obvious to you about how to prove it. But in case you don't really know, I think it's a very first step. Think about what are the variables that might be relevant and what might be the relevant, like a useful hypothesis for you to use. Okay, let's look at this example here. So these are the two critical questions you want to ask yourself. Okay, so here we're talking about n plus 1 must be a natural number. N with 1 added to it must be still a natural number, right? So definitely the relevant variable should be n. So this one may not be so relevant, right? So here, this one here may not be relevant because we're only concerned about n. Okay? And then we're just saying that n plus 1 is a natural number. We know that natural number is unbounded. So we don't really need to know about upper bound for n. So this one here is also not useful for arguing that n plus 1 is a natural number. All right, for example, right? So think about in this way. So the monotonicity rule would be very useful as a first step. You categorize your hypotheses into two categories. So think about the H1, H2 here, the rule. So H1 will be the ones that are relevant and useful. That's why you want to keep them. And for H2, so these are the ones you think that can be dropped. All right, let's now just even make it more explicit for you. So H1 will be the relevant one. I claim that this is the only relevant. All right, and then these H2, which will be this and this. So the category can contain multiple hypotheses, that's okay. So now I got a pink, I got an orange. According to the rule, I can just keep the orange. Right? So what I will do is I'm going to rewrite by the monotonicity rule. I'm going to have another sequence over here. However, this sequence here is only going to keep the H1, which contain n is a natural number, turnstile, n plus 1 is a natural number. That's only one step. In theory, you may have to go for multiple steps until you reach the end. But we are lucky because this guy here matches exactly the consequence in the rule. Remember what I said earlier? For this particular rule called P2, okay, I'll explain that what it is in a moment. So P2 over here is saying, to prove this, I just need to prove true. Meaning that this one here automatically is proved. Okay? So now let's see the correspondence. For that one, you gotta match the pattern very carefully. Okay? So for that one there, you can see n is a natural number. N is a natural number. And also you see that n plus 1, natural number. N plus 1, natural number. Right? And if you like, turnstile and turnstile. Match 100%. All right? So this one is automatically proved by P2. So this is your very first sequence proof. All right? We basically apply one single rewriting using monotonicity. And then the rewritten rule satisfies P2 as an axiom directly. So this is proved. All right? Of course, we're going to see more complicated proof later, okay, later in the semester. Okay, let me summarize very quickly, and then I'll talk about maybe one or two rules, and then we are good to go. Okay, so the general structure goes like this. You have some outstanding sequence. You start with it. And for the sequence, you have only a single goal predicates. And you may have multiple, as many as necessary, well, as many depending on your model. You know, a series of hypotheses. Okay? Step number one, you want to somehow select those that are relevant, right? The relevant ones. Okay? So for example, I might decide that maybe this one here is relevant, this one here is relevant, and this one here is relevant. Everything others, everything other than that, it's not relevant. Okay? So I can say, as a step number one, by applying the monotonicity, I simply got 1, 2, and 3 left. That'll be useful for me. And then turnstile G, the single. This typically will be the very first step. Typically, you'll see many of the proof that we do in the class, or even exercise, or even in the exam or test. Yeah, you gotta do monotonicity first. Just make it simpler. And then it's a little bit like a recursion process when you try to trace recursion in Java. So you're just going to apply as many inference rule as you have, if you have to. So maybe after some inference rule R1, after another inference rule R2, and then keep going until you reach some inference, you reach some sequence over here, a little bit like this, which will match the pattern for some axiom rule. Okay, that'll be the terminating thing. So this will be A. Okay, so this will be more like a base case. Or think about the A here is really some axiom rule, where we simply just got some consequent here and with empty antecedents. All right. All right, let's now do a little bit more. Okay, 10 minutes. Okay. Stare at this rule for a little bit. And then I'll ask you some question just to help you. Right? The rule name is called OR_L, but I'll explain exactly what that means. There's some naming convention the author in the textbook apply, which is okay. You know, I'll explain to you, but it's not too bad. But try to look at this rule over here. Okay. Okay. And here's my question. Multiple choice. Does this particular rule called ORL help us? Okay, A or B? A it can split one sequence to prove into two sequence to prove. This is not like a good idea. You wanted to prove one, but now you need to prove two. Anyway, I'll let you decide, okay? B, combine two sequence to prove into one sequence to prove. Might seem very confusing. Yes, that's why you gotta be very clear about the definition, right? So I'm basically asking this. Doing this, am I trying to say, rather than proving this, I want to prove these two? What am I saying? Rather than proving these two, I just prove this. All right? All right? The definition we already went over, right before the break. Maybe after break, I forgot. Anyway, A or B? B? A? Okay. Yeah, maybe I should put something like this in the test or exam, right? Doesn't seem to be the consensus, okay? Guys, the question, be careful, okay? This might be kind of counterintuitive. Now will be the time to start getting yourself used to this. The answer is A. All right, let's see. Let's go back to the basics, all right? This is really important. This could be one of the confusing ones, so let's spend more time, okay? So remember when we first talk about the syntax, we say consequence C and antecedent A. We say that to prove C, sufficient to prove A. Let's do some pattern matching. C here, C here. A here, A here. So what we are saying is, in order to prove this C here, it would be sufficient to prove A. However, A itself contains two sequences instead. So that's why A here is the right way to say. In order to prove a single sequence in the pink, we can split that into two sequences instead. Okay, let's visualize this a little bit. Okay, so and then the way to see this is this, and then I'll do a little bit more explanation too. Okay, how do we present this? First of all, let's start with this. Okay, we have a sequence here, and then we got H, P, or Q. Turnstile, R. So horizontal way and vertical way, right? That one shouldn't be too bad, right? But let's now do a little bit coloring, okay? So think about this one here. So we got H, and also we got P, and also we got Q. Oh, sorry. Q here. And also we got R, right? We got different things. And now if I apply the ORL rule, ORL, let's do pattern matching very carefully, okay? So what I will do is, let's now go back to this. Oh, sorry. Let me just wipe it out, okay? Just easier, okay? So let me now do the following. Okay, let me just repeat the color, okay? So we got H, and we got P, and then we got Q, and then we got R, all right? It is saying that it will be sufficient to prove two things instead, so two sequences independently. So that one there is going to be split into two sequences. Sequence number 1 and also sequence number 2. All right. That one there is saying, that's not, okay, let me also explain this particular naming. Okay. OR over here tells me that it's more, the rule is about conjunction, disjunction. And the L over here is equivocal, right? It tells me that the disjunction appears to the left of the turnstile. You can see the disjunction here appears to the left of the turnstile. That's exactly what it is trying to say. The OR appears to the left of the turnstile. All right? Let's now try to see, okay? So for the first sequence right here, okay? So what we have to do is we have to get the H, we have to get the P, and then we have to prove the R, okay? Think about we split P to here and split the Q to here separately, okay? Because you can think about this hypothesis, what we can assume is either P or Q. So assume them separately, right? So what we have is, so we have H and then P, turnstile, R. So think about what we have is H and also P and then R, right? You can see H, P, and R. The next one will be H, Q, and R, basically. Okay, let me write it down. So we got H and then Q, turnstile, R. So H and then Q and then R. So the big picture is, whenever you got any hypothesis, that's actually a disjunction. In that way, you can assume P and Q separately. So you split that into two sequences. One of them is going to use the left disjunct. Okay, so again, let me just get this one here. So you can think about the P here is split to the P right here. And the Q here is split to the Q right here. Everything else stay the same. The H exists in both. And also the R, the goal, exists in both. So this tells you that an inference rule may either try to rewrite, let's say here. In this case, it may try to rewrite a single sequence as another single sequence. It may tell you that the single sequence you have already is provable. Or it might also split a single sequence into two of them to prove. So now what we should continue from here is to prove this one here and prove this one here. So in some ways it's like a tree. That's why we say it's a proof tree. Question.
So the assumption is P and Q, when it's in like the bottom end, you have to prove both of them.
It's a very good question. Yeah, yes, that's correct. So your fellow student is thinking ahead, which is nice, okay? Hypothetically, right? Not really hypothetically, just look ahead. Let's say here, if we got some H, and then we got P and Q, okay? But that's something we'll see later, okay? So now we want to prove 1 and 1. What we can do is split that into two things, H and P, and another sequence, H entails Q. It's possible, yes, but something we'll see, yeah. Interestingly, you will actually see OR. Okay, one more thing, and then I will let you guys go earlier, just after this. Okay. So we have over here OR-L. You will also see OR-R. And also you will see AND-L, and also AND-R. So this is systematic naming there. So R and L over here just tells you where do you see that conjunction or disjunction. To the left of the turnstile or to the right of the turnstile. All right. Guys, thank you so much. Let's finish earlier today. So basically, we covered the very important details over here about inference rule. When we come back next Tuesday, we're going to dive deeper into using this. All right. Thank you.